Okay, good morning, everyone. Before we get started, I think someone left their lunch here on Monday, so if this is your bag, come and claim it. Okay, we are moving on to linear systems of ODEs today. On Monday, we went through ODEs, so ordinary differential equations, when we just have one variable. And these are good when we have very simple populations, very simple systems that we want to model. But if we have some heterogeneity, some variation in those populations, typically we want to use systems of ODEs. And we can have linear and nonlinear systems. We're first going to talk about linear systems, and then we're going to talk about nonlinear systems next week. The good thing is, in the midterm, in week 10, we're only going to do linear systems. Nonlinear systems, although it comes before the midterm, will be in the final. Okay, so this is essentially the last set of material that you need to learn ahead of the midterm. Okay, I'll talk more about the midterm a little bit closer to the time. So a lot of the stuff that we'll talk about with linear systems will apply to nonlinear systems as well. So we're going to be drawing lots of things called phase planes. And phase planes are essentially extensions of the diagrams that we were drawing the other day. Those are phase line diagrams. And we were just in one dimension. Now that we're in 2 dimensions, we're going to be talking about phase plane diagrams, okay? Now, with linear systems, these are essentially very similar linear systems of ODEs. These are very similar to what we've looked at before when we did our population models much earlier in the course, okay? Remember, we had models of like juveniles and adults and thinking about how those populations change. Those were linear systems, but they were difference equations or recursion equations. So we would write those in this form here, something like this, a vector, a population vector xn, so that's the population in time or year n. We'd have a matrix A, we would multiply the population by that matrix, and that would give us the population in the next year. So we're making these discrete jumps from year to year or from generation to generation in these models. We're going to be doing something related to this, but now we're going to be looking at continuous time. So rather than going from year 1 to year 2, year 3, we're going to have our dx dt, talking about our instantaneous rate of change for our population. Okay, but a lot of the things that we know will apply with some key differences. Okay, so we can take our system of equations and we can write it in linear form, just like we did before, using a matrix that has our coefficients. And we can think about equilibria and stability of these things. Okay, so a really key difference between the population models that we looked at before and the ones we looked at now. Now that we're in continuous time, when we talk about equilibria, fixed points, steady states, some point that you go to and you stay there, or at least if you start there, you stay there. Previously, we would be looking for vectors x star. These should be vectors. Let me put little arrows over them. We would look for x star such that if we take our matrix, multiply it by x star, we get x star again. Okay, this would be an equilibrium in those discrete time systems. In a continuous time system, you have an equilibrium x star here. When you take your matrix and multiply it by x star, you get 0 vector. Okay, this is because we're in continuous time as opposed to discrete time. Okay, so you need your dx dt to be equal to 0. We can also talk about stability. So we talked about stability in 1 dimension on Monday. Essentially, things that move towards our equilibrium mean that equilibrium is locally stable. If we move away, then we're unstable. But we have things being a little bit more complicated when we're in 2 dimensions. When we're 1 dimension, we just had unstable or stable or nothing happens. Now we have a range of different outcomes. We can have things called saddle points, stable and unstable nodes, and then stable spirals, unstable spirals, and centers. Okay, so when I talk about classifying equilibria, I mean classifying them according to these different 6 outcomes that you can have. Okay, so this is an example of a phase plane. It's quite messy. I went through this in the video. The arrows, the blue arrows, are telling us if we are at that point in that combination here of x1 and x2 in this phase plane, where do we move next? Okay, what's the direction of change? Okay, so we've got our x1 on the horizontal axis, x2 on the vertical axis, and then these lines that are highlighted are things called nullclines. Okay, nullclines are really important because they tell us when either, in this case, dx1 dt is equal to 0, or dx2 dt is equal to 0. And if they both, when they intersect, we get equilibria. Here in these linear systems, we're always going to end up with equilibria at our origin. Here, so they're going to intersect the origin. We can then think about the direction of change on those nullclines, and that will tell us what type of stability we can have, okay? So it wasn't drawn very well in the video because actually these trajectories should never cross, but we can then pick points and follow these arrows and think about what happens as we cross our nullclines, and that will tell us where we end up in the long term. Okay, so again, this is all about understanding what happens in the long term. Do we move towards a point? Do we move away from it? Are populations growing or shrinking, and so on? Okay, so I'll go through some of these. So we've got some examples in the problems. I won't dwell on them too much here, but if we have a linear system that we can write in this matrix form here, we've got a matrix A of coefficients. Our dx dt is equal to A times by X, where X is our population vector. We can work out our nullclines just by expanding by each of these rows. So if I expand by this first row here, I have 0 times by x1 plus 1 times by x2, which is where this bit here comes from. In this case, it's just x2. So what this is telling me is that when we have x2 is equal to 0, that gives us a nullcline. So this is just a line. And because dx1 dt is equal to 0 on that nullcline, that means that we're not moving left or right at all. We can only be moving up or down. So that simplifies understanding what's going on in these phase planes, because you're not moving left or right, you're just moving up and down. So you need to just figure out which way that arrow is pointing, okay? Likewise, if we set the second row equal to 0, we know that dx2 dt is equal to 0, which means we're not moving up or down. We have to only be moving left or right, okay? So again, we can solve this by expanding that first row equal to 0, sorry, second row equal to 0, rearranging it, and it gives us a line. In this case, x1 is equal to x2 over 2. And we know on that line, we're only moving left or right, okay? So if we then plot those lines, so this was the line x2 is equal to 0, this was the line x1 is equal to x2 over 2. We see they intersect at the origin. That's our equilibrium here. That's when both of our nullclines are equal to 0. So that's our equilibrium. And then we can look at each of these nullclines and see what direction we're moving. And we know that we're either moving horizontally or vertically on those nullclines. All we need to do then is substitute in or look at our nullclines and see what sign they have. So we don't care about the values that come out of this here. We only care about the sign. So when is it positive? When is it negative? Okay, we'll go through an example of this in a moment. So there are different examples. There are saddles, there are nodes, and there are spirals. Those are the things that we're going to talk about. As we're going to go through these in class, I won't cover them again here. Any questions before we move on to some problems? Yes. As in if it goes left or right, or whether it goes horizontally or vertically. Okay, so if we go back up to here, to this case here. So let me just get rid of my highlighting a second. If we consider the first row of this matrix, which I've highlighted there, so the 0 and the 1, and we expand by that row, we're going to get 0 times by x1 plus 1 times by x2. That's just expanding with matrix rules of multiplication. We have a nullcline whenever our dx1 dt is equal to 0 or our dx2 dt is equal to 0. So if we set that dx1 dt is equal to 0, that's the same as setting this first line equal to 0. So that tells me that we have a nullcline when x2 is equal to 0. And that nullcline x2 is equal to 0 corresponds to when dx1 dt is equal to 0, because that's what we set it equal to 0. Now, because dx1 dt is equal to 0, that means that we're not moving left or right. We can only be moving up or down. And likewise, when we do the second row, if we expand by the second row and set that equal to 0, that means that our second variable is equal to 0. If we set that up as our vertical axis, then we know that we can't be moving up or down because there's no change in in x2. Does that make sense? Okay. Any other questions? Okay, let's do some problems. Okay, so there are some problems on here that I'll leave to the end, or if I don't have time to go through their exercises. This first problem here is just classifying these different systems. making sure that you're familiar with the terminology autonomous, non-autonomous, linear, non-linear, and homogeneous or non-homogeneous. So just to recap those quickly, a linear system is a system that we can write our, in this case, our x's and y's in matrix form. So we can put our x and y in a vector, and we're not going to have things like x squared or xy's, okay? So there are always linear coefficients in front of those, our x's and y's. Homogeneous basically means that we can write it in the form dx dt is equal to ax. If it's non-homogeneous, then we have a constant vector like this. And if it's autonomous, that means that we have no dependency on time on the right-hand side. So there's no t's on the right-hand side. If it's autonomous, then we have no t's. Okay, so non-autonomous means we have t's on the right-hand side. Autonomous means that we don't have t's. Okay, so when we're solving our phase planes here, we're only going to be talking about systems that are autonomous. There's no dependency on time on the right-hand side. They're linear. In this case, we're not going to be doing non-linear systems just yet. And they're homogeneous, which means that we don't have this G term here. Okay, that's just a classification question, so I will leave that as an exercise. What I'm really going to try and focus on today, because we're going to be doing lots and lots of phase planes, both for linear and non-linear systems, is getting you thinking about nullclines and practicing doing those. Okay, so because there's lots of emphasis on this, I will focus on those. Okay, so here we've got some examples of some different phase planes for whatever these systems are. We don't know what these systems are. We've just got the phase planes. We want to try to understand what is the stability of our origin. Okay, so in each of these cases, these green dots will represent our equilibria. That's because these purple lines, you can't see it too clearly on here because they're purple. These purple lines are our nullclines. So this purple line going horizontally in this case corresponds to when dx1 dt is equal to 0. So if you notice along that line, all of our arrows cross through that are going vertically. Okay, and then if we compare it to this nullcline here, that's when dx2 dt is equal to 0. In that case, all of our arrows, as they cross through that, they're going through horizontally. Okay, so those are our two nullclines. With a phase plane like this, these arrows, they're called a direction field or a vector field. What we're essentially doing is we can take a point, say, I'll draw it in a different color, let's go pink. Okay, we can take a point, suppose this is our starting condition, okay? Our starting value of x1 and x2. What we're doing is we're essentially just following these arrows, okay? So we move a little bit this way. Now we can think of this as our next point here. We move a bit here and carry on and carry on. And if you connect all these things up, you end up with a trajectory, and that's telling you how x1 and x2 are changing, okay? So we could choose different starting points, and we end up getting slightly different trajectories. I'll draw arrows on these to indicate where we're going. Maybe we start over here. Here, in this case, we cross this nullcline here. When I cross that nullcline, I'm going horizontally to the right. I'm getting pulled that way. So you see in all of these cases here, we're getting pulled in this direction up to the top right. Suppose that I start down here, do it in a different color. Let's go to orange. If I start down here, I start following these arrows, and I cross a nullcline here horizontally, but now I'm going in the other direction, and I eventually get pulled down here. Likewise, if I start over here, I go in this direction. So this is known as a saddle. Its origin is a saddle. Technically, it's unstable, but saddles are always unstable. So what a saddle means is that you get pulled towards the origin in one direction and pushed away from it in the other. Okay, so we can see that if there's a special couple of lines on here. If you look at these arrows that I'm highlighting here, in fact, they extend all the way this way. You see those arrows are pointing in the same direction. All the other arrows are curved, right? And these arrows here, they're all straight. Likewise, there should be another one somewhere here. It's probably not drawn on. You can't really see it, but there would be arrows here that are perfectly straight as well. Okay, they're not curved. We'll talk about these later on in another lecture, but these are called eigendirections. Okay, so we're going to be doing things with eigenvalues again. Remember that our eigenvalues, when we have a matrix, our eigenvalues are telling us if we take a matrix, times it by an eigenvector, we get an eigenvalue times by that eigenvector. So you just get a multiple of it, okay? And so what's happening, these eigenvectors are stretching our system in these directions, okay? So one of our eigenvectors is pulling us in one direction, the other eigenvector is squishing us in the other direction. And so we get pulled towards the origin in this direction or this direction. And we get pulled away from it in this direction and this direction. Okay, so our eigenvectors and our eigenvalues will be really important for solving these because they're pulling us and pushing us in different ways. So when it comes to solving these, we can draw phase planes. We can also look at our eigenvalues and our eigenvectors to tell us what's going on in the long term. Anyway, that's a little aside for this. In this case here, this phase plane, because we're being pulled away and pushed in towards the origin, we have a saddle. Okay. Okay, this one here. Kind of obvious. This is a spiral because if we take a point, say here, and I follow those arrows, I'm spiraling away from the origin in this case. Okay, so regardless of where I start in this case, as long as I don't start at the origin. So because the green dot is in equilibrium, if I start on that green dot, nothing happens by definition. If I start a tiny bit away from it, I spiral away in this case. So this is an unstable spiral. Again, like before, we had our nullclines that intersect at the origin. And we can think about, if we wanted to construct this phase plane, we can think about how our direction field changes as we cross our nullclines. Instantly, there's nothing special about picking, well, there is something special about picking the nullclines. That you could pick any point in this space and work out your direction field from that. The reason we choose the nullclines is because by definition, we know that we're either moving left or right or up or down. So it takes out one of the directions, okay? We don't need to worry about if we're moving up and to the right or down and to the left and so on, okay? So that's why we construct things using our nullclines. Okay, so in this case, we've got a spiral. In this case, it's an unstable spiral because we're moving away from the origin. If everything was spiraling into the origin, then it'd be a stable spiral. We can also have things called centers. Centers are a little bit complicated in some sense from a mathematical point of view because they are what's known as structurally unstable. They are at the point between a stable and an unstable spiral. And in a center, you'll have something that looks like this. Regardless of where you start, you just keep moving around in an ellipse. Okay, so that is a center. This last one here, let's pick some points. I'm going to pick this one up here. So if we start up here, this is our initial condition. We move in like this. If I start over here, again, moving towards the origin, regardless of where I start in this case, I always end up at the origin eventually, okay? So because we approach this without spiraling in, this is a node. And in this case, it happens to be a stable node. And it's stable because we're moving towards the origin. If we had trajectories just moving away from the origin, it would be an unstable node. There are also things called stars, but we're not going to talk about stars in this course. As far as we're concerned, we'll just focus on nodes and spirals and saddles. Okay. Before I move on, any questions about these phase planes or anything I've talked about so far? This is another question I'm going to leave as an exercise, or if I've got time at the end, because I really want to focus on phase planes and making sure that you guys have practice of this. This example here, if you want to work this out in your own time, we have a model for gene regulation, and we've got these different variables, M and P, telling us about the amounts of mRNA and protein in a cell. And we want to write this problem in this form here. dxdt is equal to ax, so A is our matrix, x is our population vector, so we'll have x is equal to, say, M and P. And we're going to have this G term as well, this other vector, this constant vector. The reason we have this constant vector is because we have this constant term here, so we have to add this on. So in this case, we have a system that's non-homogeneous. Okay, and we're asked here to show that the fixed point is a half. So how do we do that? Well, we can just do some substitution. So you can substitute a half into this equation and into this equation, and you should get 0 and 0. You can also check our right-hand side by writing our matrix in this form AX plus G and setting your X here to be a half. Do AX plus G and you should get a 0 vector, okay? And that will confirm that this is indeed a fixed point of the system. So have a go at that in your own time, or if we have time at the end. Like I said, I want to focus on phase planes today. Okay, before we actually start like trying to construct one from a system, let's think about what's actually going on here at each of these points. Okay, so we've got some system here, dx dt is equal to -1, 0, 0, 2. So this is our matrix A times by our vector x. Okay, so what's actually going on here? So we can think about taking each of these different points here and working out what is our dx dt at each of these different points. Okay, so if I take 0, 0, so if I look at -1, 0, 0, 2 times by each of these things, so in this case 0, 0, I'm just going to get a vector, and we're always going to end up with a vector here. So x is a vector. So we just end up with a 0 vector. So that means that if I start at the origin, I don't actually move anywhere. I have a 0 vector. I'm just going to represent this as a point. We can't draw an arrow with length 0. Okay, let's think about 1, 0. We take 1, 0. So if we now look at this, again, we're just doing matrix vector multiplication here to work out what our vector is. So in this case, we're going to have -1, 0. So that tells me if I start at the point 1, 0, so that's this point here. And because my vector for dx dt is -1, 0, that's telling me I'm moving 1 unit to the left and 0 movement, 0 units up or down. So I can think about an arrow pointing from there, in this case, 1 unit to the left, no units up or down. Okay, let's carry this on for these other points here. So let's see what we've got next. We've got 0, 1. In this case here, we'll have a vector 0, 2. So if we start at the point 0, 1, so that's this point here, we're going to move 0 units left or right and 2 units up. So we have an arrow that looks like this. For the sake of time, let me just fill in these other ones. So if we start at -1, 1, so if we start at this point here, we end up with a vector 1, 2. So that's telling we move 1 unit to the right and 2 units up. So I'll have an arrow that looks like this. And the last line, if we start at 1, 1, we end up with a vector -1, 2. So if I start here, I go in this direction. Okay, I've drawn the arrow a little bit shorter just so we can see the arrowhead. So this is really all we're doing when we're constructing a phase plane. We're thinking about, if we're starting at all these different points, where are my arrows pointing? We don't actually care about the length of these arrows, which is why in these phase planes here, you know, that all of these arrows have been rescaled so they're roughly the same length. Okay. The reason we don't actually care about the length of these arrows when we draw our vector fields, our direction fields, is because as soon as we move a little bit, because we're in continuous time, our trajectory can change. So if you think about a curved trajectory like this, which is what the kind of things that we had above, that's really composed of lots of infinitesimally small little arrows like this, okay? So you move a tiny, tiny bit, and then we change direction again, okay? So realistically, if we start at this point here, we don't make a big jump up here like that. That's our direction at that moment in time. If we're going to follow a curved trajectory, as soon as we start moving, that direction can start changing. Okay, so that's why we tend to rescale these things, and so we don't have these arrows crossing as well. What's really going on is it's telling us what is the instantaneous change or direction of change. Okay, so if we think about a curved trajectory like this, we have lots of little arrows that will be joining up together. Okay, so if we take our same matrix now, let's have a think about constructing a phase plane. Okay, I'm going to write this out just to make sure it's clear. So we've got, if we expand this matrix, we're going to have dx1 dt is equal to minus 1 times by x1 plus 0 times by x2. So that's one of my equations. So my dx2 dt is going to be 0 times by x1 plus 2 times by x2. So that's me just expanding that matrix on the right-hand side by the first and the second rows. Okay, so these are telling me the rates of change for my x1 and x2 variables. Okay, you can imagine these things, maybe it's describing animal movement and their positions in space. Okay, so we can take positive and negative values if we're thinking about if we have a reference point and where we are relative to that reference point. Okay, so when we're constructing a phase plane, the first thing we need to do is think about our nullclines. Nullclines are basically kind of like level curves. As you move along that, the value doesn't change. In this case, the value is 0. Okay, so if it helps to think about level curves, think about nullclines as being a little bit like your contours on a map. As you move along that, in this case, your dx1 dt doesn't change, it's 0, and likewise your dx2 dt might not change either. Okay? Okay, so we're going to have two nullclines here because we have two variables and they're both linear. When we do nonlinear systems, we can have more variables because we won't have linear equations. So when do we get dx1 dt is equal to 0? Well, all we need to do is we need to set this equation here equal to 0. So this only occurs if x1 is equal to 0. So what's the line x1 is equal to 0? I'm going to draw this in colors. Let's do it in blue. Okay, so x1 is equal to 0 is just this vertical line here along this axis. Can't see it super well there, but there's a blue line along that axis. Okay, that's my line. X1 is equal to 0. This vertical axis is x2, and I'm calling this horizontal one x1. This blue line is x1 is equal to 0, and that's when dx1 dt is equal to 0. I realize I've drawn little arrows over the top of these x1s and x2s here. They shouldn't have arrows over them, sorry. Because they are not vectors. Okay, so on that line there, we know that dx1 dt is equal to 0. That tells me that I must be going up or down. My arrows, my direction field is going up or down as I move along that blue line. Okay, and that's because we know that we can't be moving left or right because dx1 dt is equal to 0. Okay, I'm not going to draw them on here because of the vertical line, and we'll coincide with it, but we'll get to that in a second. Okay, our second nullcline, we set dx2 dt is equal to 0. So that's just going to be this equation here. If we set that equal to 0, that only occurs when x2 is equal to 0. And because x2 is equal to 0, we can't be moving up or down, or sorry, dx2 dt is equal to 0. We can't be moving up or down, which means that we must be moving left or right on that nullcline. I'm going to draw this one in red, just so it's a little bit clearer. That'll give me a straight line. So if we draw the line x2 is equal to 0, that's just a horizontal line here. So this is my line, x2 is equal to 0. And on that line, we know that dx2 dt is equal to 0. So there's no change in the vertical direction on that line. Okay, so once you've found your nullclines, what do you need to do next? Now we need to think about our direction field. Okay, so we need to work out on those 9 nullclines, are we going up or down? Are we going left or right? So what we do is take them in sequence. and we think about what's going on if we're on, let's say, x1 is equal to 0. So this is this first nullcline here. If we're on the line x1 is equal to 0, when do we go up? When do we go down? So we know that we're going up or down because dx1 dt is equal to 0 by definition, because we're on the nullcline. What we can then think about is what's going on with dx2 dt when we are on this nullcline. Because dx2 dt is going to tell us if we're going up or down. We need to think about what is our equation for dx2 dt. And we get this just by thinking about this second row here that we've expanded. So that's this, I'll just re-highlight it again. It's this equation here. That's telling us what's changing for x2, our second variable, and we can think about what happens on this particular nullcline. Okay, so we know in this case, it's equal to 2x2. So it's telling me that my x2 variable, the instantaneous rate of change, is equal to 2 times whatever that variable is. So that tells me that dx2 dt is going to be positive if x2 is positive. I don't care about the magnitude of the change, I just care about the sign. And if dx2 dt, to get dx2 dt to be negative, we need x2 to be negative, okay? That means I can draw on some arrows here that when we're above the axis, so when x2 is positive, our arrows are going to be moving up. When we're below, our arrows are going to be moving down. You notice we have an equilibrium here. When we move through an equilibrium, the signs, the direction of our arrows is going to change, okay? So if you work out what the direction is on one side, that's automatically going to give you the direction on the other side. You definitely should not end up with a case, for all the things that we're going to look at in this course, you should not end up with a case that looks like this. Okay, the arrows should change direction. It is possible that they don't change direction, but we're not going to cover that in this course. Okay, so that's this one direction here. We now need to think about our second nullcline. We do exactly the same. So on our second nullcline, that was this nullcline here, x2 is equal to 0. Let's think about what happens on this nullcline. We know that dx2 dt is going to be equal to 0 by definition. But what happens to dx1 dt? Well, our dx1 dt was up here. Again, this is just coming from our original matrix. dx1 dt is just equal to minus x1. So how does the sign of dx1 dt vary? Well, that tells me that dx1 dt is negative if x1 is positive, and it's positive if x1 is negative. Okay, so it has the opposite sign to x1. In other words, my rate of change in variable 1 is equal to minus whatever that variable is. So that means I can draw my arrows on here. On this nullcline here, dx1 dt is negative, so we move to the left when x1 is positive, and dx1 dt is positive, so we move to the right when x1 is negative. And the great thing about this is, by thinking about our nullclines, we don't have to draw in every single arrow possible in this phase plane. We can deduce what happens just by what's going on with our nullcline. So we know in this top region here, we're going to be still moving a bit to the right, and we're going to be moving up. So that means the net change is going to be something like this. Again, we can think of in this top right quadrant here, we're going to be moving a bit up and a bit to the left. So our net direction, if I draw that properly, will look something like this. And I can do this for these other regions as well. So here we'll be going down to the left. Here we'll be going down to the right. Okay. You don't need to draw these additional ones in here that I've just done now. That's just to emphasize what's going on. Okay, so we have all the information we need now. If we imagine our starting point here, it's useful usually at the end to draw on some trajectories to see what's going to happen. If this is our starting point here, we're going to be moving up and to the right. Okay, so maybe we start off moving in like this. Eventually, we're going to be pulled up in this direction here. Okay, if we start off over here in this top right quadrant, we move in and up to the right. Twice here, we'll move in and down to the left. Here, in towards the origin, but then down to the left. I said down to the left a minute ago, I meant down to the right. Can anyone tell me what the stability of my fixed point, my origin is here? So it's unstable. If I ask you to classify it, how would you classify it? It's a saddle. Okay, great. This is a saddle. This process here of working out what the nullclines are and then the direction field on the nullclines, that we will be doing a lot of. Okay, so I encourage you to practice this and go over this because we do it in linear systems. When we deal with our nonlinear systems, we don't just have equilibria at our origin, and we can have multiple equilibria, but we draw our phase planes in essentially the same way. We find our nullclines and then we look at the direction field on those nullclines. Okay, so it's more complicated in those cases, but learn the basics here using these systems. Key thing, find your nullclines, then think about on each of those nullclines, what is happening to your other variable? When is it positive? When is it negative? Okay. Okay, we've gone through that in quite a bit of detail. I want to give you guys a few minutes to have a go at practicing this one here. Okay. Have a go at practicing that and I'll go around and answer some questions. Okay, guys, I'm going to run through this just because there's only a few minutes left to make sure it makes sense. It will take a bit of practice. I appreciate that. Okay, so we have this matrix here, -3, -1, -1, -2. To work out our nullclines, we just expand by this first row and then expand by the second row. So our dx1 dt is going to be equal to 0 when we expand by this first row and set it equal to 0. So we're going to have -3x1 minus x2, I'll zoom in over here, -3x1 minus x2 is equal to 0, which we can rearrange. I'm going to rearrange it in terms of x2 here. You can put it in whichever order you want. You could rearrange it in terms of x1 if you want. The reason I tend to put it in terms of the second variable is because we tend to put our first variable horizontally and our second variable vertically, and just makes drawing it a little bit easier. Okay, so that's our first nullcline. And then our second nullcline, we do the same, but for the second row. Okay, so we expand by the second row here. dx2 dt is equal to 0 when we have -x1 minus 2x2 is equal to 0. We can rearrange this in terms of x2. x2 is equal to -x1 over 2. Okay, so you've noticed I put these colors here, the greens and the reds. I like to color code my phase planes because it helps to make sure that I'm drawing things correctly. So if I draw those two nullclines, I have these two lines here. Okay, so on the green line, we have dx1 dt is equal to 0. So that means we're only moving up or down. So at this stage, I can actually draw on some vertical lines because I know that when I cross that nullcline, I'm moving vertically. I don't know at the moment whether I'm going up or down in these different places, but I know that we must be moving vertically. On the other nullcline, dx2 dt is equal to 0. So I know that I'm moving horizontally. So at this stage, I like to draw on, if I can, vertical and horizontal lines to make sure that I remember which nullcline I'm working on, okay? Okay, at this stage, I now need to think about my direction field. So let's think about this first nullcline here, the green one. So that's when x2 is equal to -3x1. Okay, so the green nullcline, we know we're moving vertically because dx1 dt is equal to 0. So there's no change in my x1 variable, only change in my x2 variable. So dx2 dt is equal to, well, we just expand our matrix. Okay, so what do we have? We had -x1 minus 2x2. And now we substitute in this into here to eliminate one of my variables. Now I could eliminate x1 or I could eliminate x2. It doesn't matter. It's not going to change the direction of my arrows. It will just change whether I'm doing it in terms of x2s or x1s, okay? So in this case, I'm going to eliminate let's eliminate x2. So we have -x1 x2 is minus 3 times by x1, so we end up with plus 6x1 here. So all I've done is I've eliminated my x2 by substituting in this nullcline into my dx2 dt equation. So this is now just 5x1. So what does this tell me? This tells me that dx2, think about this here, dx2 dt is going to be positive if x1 is positive, and it's going to be negative if x1 is negative. So let's go back to my phase plane here. I'm on this green line, remember? dx2 dt is positive, that means we're going up if x1 is positive. So x1 is positive on the right-hand side, so those arrows must be going up. dx2 dt is negative, so we move down when x1 is negative. So these arrows have to be going down. Okay, we can do the same for the second nullcline. So here we're going to have minus 3x1 minus x2. Substitute in our nullcline into my equation for dx1 dt. In this case, I'm going to eliminate x2 again. So we get minus 3x1 plus x2 over 2 is minus 2.5x1. So here we can tell that dx1 dt is going to be positive if x1 is negative, and it's going to be negative if x1 is positive. Okay, so it's the opposite sign to x1. So now we're on this red line here. If x1 is negative, dx1 dt is positive, so that means we move to the right. And if x1 is positive, dx1 dt is negative, so we move to the left. Okay. We have this one intersection here because we're in this linear system. We can now think about what goes on if we start on these different trajectories. Suppose we start up here, moving down and to the right until we reach our fixed point. If we say start here, we start moving up and to the right, we cross this nullcline vertically, and then we start moving to the left here. Okay, so whichever way you pick, you end up moving towards the origin. So can anyone tell me what this is? It's a stable node. We'll be covering lots more of these, don't worry. Sorry, question here? Come and ask me in a second, it might be easier. Okay, guys, I'll see you on Friday.